Trace tables and time efficiency are essential aspects of the design and testing phase in computing, ensuring that algorithms function correctly and operate within acceptable performance constraints. A trace table is a systematic way of following an algorithm step by step, recording the values of variables at each stage to identify logic errors. Time efficiency, on the other hand, evaluates how quickly an algorithm executes relative to the size of the input, helping developers optimize their code for better performance. Both techniques contribute to the overall reliability and effectiveness of software development. A trace table is a useful tool for debugging logic errors in an algorithm by allowing programmers to manually track how data changes as the algorithm progresses. A logic error occurs when a program runs but does not produce the expected result due to incorrect implementation of its logic. Unlike syntax errors, which prevent execution and are detected by compilers, logic errors do not generate error messages, making them more difficult to identify. By using a trace table, a programmer can systematically follow the flow of an algorithm, checking each step to ensure it behaves as intended. To use a trace table, each variable involved in the algorithm is recorded in a table format, with its value updated as the algorithm runs. This manual simulation helps highlight any discrepancies between the expected and actual values, revealing where an error might have occurred. For example, if an algorithm is meant to sum the values in a list, but mistakenly resets the total to 0 at the wrong point, a trace table will show exactly where this mistake happens, allowing for quick correction. By breaking down the algorithm into individual steps, trace tables provide clarity, ensuring that every calculation, loop iteration, and condition is working correctly. Trace tables are particularly valuable in testing algorithms that involve loops and conditional statements. When a loop executes multiple times, it is easy to lose track of how variables are updated with each iteration. A trace table provides a clear visual representation of these changes, making it easier to spot off-by-one errors, infinite loops, or incorrect exit conditions. Similarly, in conditional statements, a trace table helps verify that all possible paths through an algorithm are covered, ensuring that the logic accounts for different input scenarios. This is especially important in complex decision-making structures, where multiple conditions interact. While trace tables help identify logic errors, testing algorithms for time efficiency ensures that they perform optimally, particularly as input sizes increase. An algorithm may produce correct results, but if it takes too long to execute, it becomes impractical for large datasets. Time efficiency measures how the execution time of an algorithm scales with input size, helping developers choose the best approach for solving a problem. The efficiency of an algorithm is often expressed using Big O notation, which describes the relationship between input size and the number of operations performed. Common complexities include constant time, logarithmic time, linear time, and quadratic time. An algorithm that runs in constant time, denoted as O1, executes in the same amount of time regardless of input size, making it highly efficient. A linear time algorithm, ON, scales directly with input size, meaning that doubling the input roughly doubles the execution time. Quadratic time algorithms, ON2, become significantly slower as input grows, since each increase in size leads to an exponential rise in operations. Understanding these efficiency measures allows programmers to predict performance and make informed decisions about which algorithms to use. Testing for time efficiency involves running an algorithm with different input sizes and measuring execution time. If an algorithm performs poorly as the input size increases, optimization techniques may be required. These could include improving loop structures, reducing unnecessary calculations, or using more efficient data structures. For instance, searching for an item in an unsorted list using a linear search takes ON time, but using a binary search on a sorted list reduces this to O log N, dramatically improving efficiency. In some cases, an algorithm that is logically correct may still be inefficient due to redundant operations or unnecessary memory usage. Trace tables can assist in identifying inefficiencies by showing when certain calculations are repeated unnecessarily. By combining trace table analysis with time efficiency testing, developers can refine algorithms to not only work correctly, but also run efficiently. Ultimately, both trace tables and time efficiency analysis play a crucial role in software development. Trace tables ensure that algorithms are free from logic errors, helping developers verify that each step produces the expected outcome. Time efficiency testing ensures that algorithms perform well at scale, preventing slow execution times that could hinder usability. By incorporating these techniques into the design and testing phase, programmers can create robust, efficient, and reliable software that functions correctly across a range of input sizes.